Okay. Good afternoon, everyone. I hope all of you are doing well. So today we'll do that whatever we have done with in the previous class, that common emitter characteristics for a bipolar junction transistor. Now today we'll do perform that common base circuit. So after having the characteristics of common base one, if time permits, then we'll do that. We, we will study the circuit of the same BJT in common emitter mode, but we'll use we'll see the application of it as an amplifier one. So we'll try to cover this if time permits. Otherwise, we'll cover that common base one. And after this, I think you will have only one. I think you will have only one lab, and then um, uh, most probably there will be quiz or that. Maybe faculty member will decide on that one. So, okay, so do you have any query from previous class? Okay, I think you don't have. Okay, let me tell you. So in this case, it will be similar for that means common emitter mode, as already I discussed with you people, that in case of all these three different mode, that common emitter, common base, and common collector, as it is a three-port device or three electrode device, and if we consider to fit this one to a two-port model, then we need to have a common port that is common for both input and both output. So for and depend, as it is having three different electrodes, emitter, base, collector, so we can make them differently as in common. So depending on that, we have different connections. So in previous case, it was emitter was in common for both input and output, and for today we will see that base will be common for both input and output. And for this, we have to consider that this following circuit diagram. So in this case, as you can see, this is your input terminal and this is your output terminal. So in order to have that input characteristics and out means we have to study input and output characteristics. So in case of input characteristics, IE as a function of VBE and VCB, and we will make the this junction potential as constant, and we will see what is the means uh, what what will vary in the curve or variation in the curve of input characteristics as we vary the VCB for different set of VCB, and we will vary the VB, base emitter junction voltage. So basically this is input terminal and this is output terminal. Means base emitter junction will be as acting as a input terminal, and collector base junction will act as a output terminal. So in both the case the base is in common. So this is the circuit diagram for input characteristics, and this one is for output characteristics. So in case of output, we have to consider the collector current as a function of VCB and IE. And if you can remember, initially for common emitter one, it was for different IB base current, and we have plotted those graph too, and we can see what are the differences in different curve for different values of IP. So in this case, we have to vary the IE, means emitter current, for that one. So this will be the output characteristics circuit diagram. So basically circuit is same. The measuring parameter will be different. In case of output characteristics, we have to consider the output properties like output current, collector current as a function of output voltage. You can say output means junction voltage, VCV. And in case of input current is IE, emitter current, and the voltage will be across VBE, means voltage across base emitter junction. Okay, let's go to the simulation one. So basically it is having input, and so we'll do everything over here virtual lab, and after that we'll go to that multi-sim one. Okay, so as you can see, it is basically the same circuit, means whatever you have seen here in the means theory portion. So here, okay, could you please tell me once that what kind of transistor we have used here? Means they have given here. Anyone, those who are online, then they can respond or send me through chat. What kind of transistor they have used?
NPN.
NPN. Okay, good. Basically, they have used NPN. I think we have already discussed about two different type of transistors, NPN and PNP. So as the current is means arrow is directed towards the emitter, so you can say NPN transistor, because it is for say means remember analogous to consider that current will flow from positive to negative, or you can say P to N. So that's why NPN. So basically they have used a NPN transistor, and emitter in order to measure the emitter current, they have put an emitter for here, and the voltage emitter junction voltage means the junction voltage across the base emitter. Yes, that they have varied with respect to this varying this rheostat knob. So from here we can see the variation of this VB, and in case of output also there are two emitters. One is one emitter is for measure the collector current, another one is for the collector base junction potential in order to measure what is that. So first case, what we have to do, we have to make a base collector voltage constant. Means we have to make it fixed first. So let's consider it, we are keeping it as, so what is the voltage? Let's say for, we will see the variation. So you can, okay, let's say for 0.5 volt. Okay. And now we will vary the base emitter voltage accordingly, and we will see what is the. So as we can see, we have some data we are adding for the, means as we have applied 0.18 volt across the base emitter junction. So for that we will have a current in milliamps emitter current. So please remember, in all the cases, somewhere current will be in milliamps and somewhere uh, current will be microamps. So please remember that thing. So because then only if you measure all these things, then properly with proper unit, then only you will have a proper curve. Now let's okay, now for 0.36 volt we will have 1.2 milliamps current in emitter current as emitter current. Now for 0.54 volt we will have 1.6 milliamps still, and now we have moved towards higher value of base emitter junction is 0.86. For 0.86 base emitter voltage we have a current of 2.5 milliamps, and let's say it is for 1.2 volt, current is 4.1. So basically you can see the current is gradually increasing. Now for, let's check for maximum value of 2 volt, it is 13 milliamps current. Okay, now I think we can have a plot, but I don't think we will have that means different parametric plot. So for that one, we'll copy all this data and we'll plot over here. Okay, I think my screen is not visible to you. Now it is visible, right? That
Yes, sir.
plotting window. Yes. Please let me know whether it is. Sometimes I forget to switch between these two, so please let me know. So once we plot this, we can have. So basically the DAT characteristics we are having, we can refine it. The main thing is that we need a parametric plot, that all what we have done in previous case for that of mm, that common emitter mode one. Okay, so this is a nice curve, exponentially increasing as we are increasing the voltage and current. So basically this is voltage VBE, VBE, and this is IE, and the unit is milliamps, and this unit is voltage. So it is reflected. Okay, now let's have some data for different uh, collector junction voltage. So depending on that, we can have the parametric plot. Okay, now let's clear everything. Let's clear everything. Is there any problem? Okay, let me put it into 2 volt or something like that. Okay, initially, could you please remember me what was the VCB? I forgot. It was 0.5, right? Yeah, I think so. So please let me note that over there.
Yes, sir. 0.5.
Okay, okay. Thank you. Thank you. So for this case, let's say we have considered 2 volt. Okay, it 2 volt. I think it is website is not working. Am I audible to you people? Means I think network
Yes,
connection
sir.
is
You are audible.
maybe the problem is in the website.
Yes, sir. We have some problem.
Okay, let me refresh it once. I think there will be no problem. So now consider the voltage VCB as 2 volt, and we'll have the same data means that input characteristics. So in this case, VCB is 2.1 volt, and we are considering several data for VBE, for current, emitter current as a function of base current. So we will see just we want to have some parametric plot. If there is any change or not, we will see what will affect. Means is that collector base junction voltage are affecting or not? We will see that. So let me copy this data and we'll plot it over there. For this case, our voltage is 2.1. Means collector base junction voltage is 2.1. This will be 2.1. That's VCB equals 2.1. Yeah. Okay, let me plot this one with the same graph. So as you can see, there is no difference. As these things means we have done this for a common emitter one also. So basically, it is almost more or less same curve which is showing. So no, from here we can conclude that in case of input characteristics, it is more or less independent of the of your collector base junction voltage. Okay. So till now, do you have any query you can ask related to this? If you have, then otherwise we'll move to that circuit drawing part. Okay. Do you have any query?
Mm,
Okay. No issue. Okay. This was for common emitter one. Okay. Someone, I think. Okay. Thank you. Okay. Let me draw this circuit for you people. 1 second. Okay. My screen is not visible to you, right? Means that this screen constant, it was constant. Now I think, yeah, now
graph we can see.
yeah, now we are in multi-sim one. It is visible.
Yes, sir.
Okay, good. Thank you. In multi-sim we will draw the circuit, same circuit for common base one. So in this case they have applied no resistor across any of the electrode, but as already we have discussed, for lab purpose we have to apply resistor across all the electrodes. Okay, so let me draw the circuit first. Yes, we'll have a NPN. So have you tried with that NPN and PNP characteristics? Means from here, multisim one. You can explore it. Means all those things I think we have done with the NPN one. So you can try what will be the nature for PNP and something. All those variations are here. Okay. If you have not done, then you can do it. Okay, for this one, now we have to add 3 resistor across the 3 electrodes. Okay. So I have just connected R1, R2, R3 across that collector, emitter, and base junction. So we can rename them as well. So as already we have discussed in case of common emitter one. Okay, yeah, it is not there. So the base one will be in kilo ohms, and this should be in uh, no means lesser value in this case. So let them consider as 355, and this one is, let's say, 500 ohms. Okay. So we have considered this case means base current should be, we want to control base current. So in previously, or more or less you can say, as the base region is thinner with respect to that, means if you go to that diagram for any BJT, then you can see that means you can have uh, okay, basically this PNP one, I'll, yeah, this one. So if we go to the physical cross section, physical section over there, means for NPN junction or PNP1. So basically the base junction thickness of the base junction is not equal to that of that emitter and collector one. So that is why we cannot inject much more carrier in base junction. So that is also, you can say, one of the reason. And also I think you will come through different one terminology is that punch through effect or some those things whenever you will come through that basic means theory of that BJT, then you will come to know why it is kept intentionally kept thinner and why we cannot increase much the base current in higher order, higher value. Anyway, so for that one, okay, we have done only our input characteristics from here. Okay, after that we will do the output characteristics. Anyway, let me do it for. So we have to apply some voltage for two junction. This junction as well means this base, a collector base junction and also collector emitter junction. Okay, so as you can see in this case, I have considered them in same direction, means same bias. But what will be the bias for this one? Can anyone tell me what will be the bias? In case of common emitter mode, we have considered about two different region when our all of them are in reverse bias, means all of these two junctions are in reverse bias and any one of them are in forward bias. Then what, there are three regions, three regions basically we have discussed, that cutoff region, if you can remember, cutoff region, active region and also saturation region. So if we keep them in forward bias, both the case, then we'll have a saturation region. If we keep them both of this junction as reverse bias, then we'll have that of cutoff region. That things I think we have already discussed in last lab. So can anyone tell me in the what is the means the in which bias we have kept for these two junction, base emitter and base collector one?
Base emitter forward, collector base reverse.
Are you sure?
I think so, sir.
Why you are telling in this way? Because why so? That's why you are telling. What kind of transistor it is?
Uh, NPN.
Okay. Then in order to make this P, okay, let me open the circuit for emitter one, then also common emitter one. Then I think everything will be clear. Yes, if it is NPN, then what should means if we want to make it in forward bias, then what should be our circuit means? What should be the connection? me open that circuit, then we'll discuss. In the meanwhile, we can draw the circuit. Okay, it is not opening. Yeah, let me open it. So I think now it will be clear to you people why we are saying this. Means why we have this for base emitter, sorry, common emitter one, and in this case why we have this configuration. So basically, if we follow the circuit diagram that was given here, yeah, we have we have done accordingly. Why so? Yeah, now the circuit is visible to you. Only the schematic is required. Yeah, this was that common emitter one. Circuit is visible. Common emitter circuit is visible to you
Yes,
people.
yes,
Okay,
yes, sir.
good. So now you can see, in this case, this is also NPN. This is our collector base emitter, right? So in this case, base is connected to the positive terminal as base is P-type semiconductor. So P-type is connected to the positive. Then only you can say it is in forward bias, isn't it? Are you getting?
Yes, sir. Yes, sir. Yes, sir.
And in this case, it is connected to the collector, which is N-type, and we have connected to the connected the positive terminal. Okay. So from there you can comment on that it is in reverse bias. Did you follow that?
Okay, sir. Yes, sir.
So in this case, we have done this circuit, and now we will see what will be the response for that. And okay, let me rename it first. It should be VCB. It should be VCB. So no, it is VEB. This is the VEB or BE, you can say, base emitter junction. These things will vary, and this is VCB, collector base junction. And we will I don't think parametric is required, because we have seen for parametric one there is no change basically. So I think it is not required, parametric input characteristics. Okay. Yes, we have to consider, let's say we have consider the VB as 1.5 volt. Yeah, 1.5 volt VCV. And for that one, we will change the value. Now, please, as the DC sweep option is not here, so you have to note it down the values. So please help me. Any one of you, please note down the value and tell me, then I will plot it. Don't worry, we will not perform that parametric plot. So I think there will be no issue. Okay, someone is ready with to consider the data?
Yes, sir.
Good. Thank you. So DC operating point. Now let's run the circuit. Oh, sorry, we have not added any probe. We are supposed to add any probe, means what do we want to measure? So in this case, as we need, first of all, we need the voltage, VCV. These things we need. And also we need VBE, or you can put it. Okay. Okay, let's put this here because our collector is here. Across means after this register, we are having this collector. Okay. Now we need one, as in case of input, we need emitter current as a function of base emitter junction. So basically, I think we need an emitter current that should be in that direction. I think we can rotate it. So because our emitter current is into this direction, as you can see from here, current emitter current, where it is, yeah, emitter current is, it is flowing out from that emitter. Okay. Otherwise, yeah, emitter, sorry, emitter, sorry, this is for common emitter one. Yeah, this is the common base one. Yeah, emitter current is should be in this way. Okay, right. I'm sorry. Okay, so now we have this one. What is this? Yes, this is that mentioned as V2. That is the basically base emitter junction voltage, and this current is emitter current. Okay. Let me run it. Okay, so it is showing only one value. What happened to this? I don't know why it is not showing. Let me remove it and connect another voltage. We need the
So
voltage.
please move that probe towards the resistor, sir, until it shows a signal like this connect. Once it blinks red, please move towards the resistor.
Okay. Okay. Yeah, that is why. Thank you. Okay, so I think now we can have the data. Yes, V1 means that collector base junction potential, that is 1.5. Okay, for 500 millivolt. Okay, femtofarad. So I think we can increase the voltage because we have given the resistor. So I think we can have not 5 volt. Let's say at least 1 volt. Yeah. Let's say we have applied 1 volt over here. Then but thing is that if we have connected over here, it will tell me the value of this thing. Basically, that is the voltage across all those things. These two
Sir,
resistors.
please connect the voltmeter left to R1, sir. You can connect it.
Sorry.
Please place that voltmeter symbol just beside the R towards its left side.
Okay. Means say that should be similar to that of this one, right? You are telling. Okay. Now that thing we can do, but I think it will be better to study with a that with the register one, because in our lab, means in lab, real life lab, we should have some register. We should apply some register because of protection of the circuit and also current control. So many things is required. Okay. Anyway, we can do that one. No issue. Let's remove the register.
Sir, I'm not saying to remove, sir. Just move the voltmeter. I'm saying that's.
Uh,
Please connect to the end. Now you connect, sir. Voltmeter.
okay. You were
Just
telling
put,
that we have to connect it.
yeah, that two symbol. You can
Oh,
see it is blink.
okay. Yeah. Actually, I have. Yeah. That was. Okay. Let's for 1 volt. Let me check what is the effective one. It is still showing 1 volt. Okay. With respect to these things, there was some volt. Oh, as because it is in femtosecond, femto ampere. That is why. But it should not be the case. Okay, let me increase it further. Let me check once, and then still the current is in picoampere. I think we can reduce the value. And reduce the value, then and also these things too. In 100 amps and this one is at 500. Sorry. Okay. Now let me run this. Still the current is in picofarad. Is there any problem in the specification of this transistor that we have to mention? All these things here. Okay, let me do it means by removing the resistor. I think we can have the similar study for that VLab one. Okay, I don't know why it is not working, but okay, still check. Let me check it once. Okay, now run it. Still the current is in picoampere. It should not be the case. Picoampere is very less. In this case, if we run it, then what was the current? It was in milliamps. Microamps initially, then if we increase the that IB is in microampere and IC is in milliampere. So in this case, what was the problem? Means what is the? I think what is the problem? If anyone can help me out, please help me regarding this. I think there is a problem with that transistor specification. Yeah, this thing is 10 power minus 16.
Sir, in that diagram, both are reverse bias, no, sir?
Yeah, both.
Isn't that a problem?
Yeah, both are reverse bias.
Okay, okay.
Yeah, yes, you are correct. Both are in reverse bias. We should keep it at least one in active. Then only we can have. Yes, that was the. Yes, we have. Actually, I'm sorry, I forgot to. We are already discussing that things, right? Base. Yes, we are discussing this thing. Okay, let me undo everything. And that is why we are having the current in pico or like that, a pico ampere. Okay, now we have to apply a source, and we'll reverse it because our this junction should be means connected. This is P, so P should be connected to that of positive terminal of the positive terminal of the battery. So that is why you have to consider this. Okay. I think there will be. Yes, now it is in nanoampere. And if we further increase it, I think we'll have changing. Let me check it once and we'll just, yeah, it is in microampere. And now it is increasing because of this resistor, there will be drop. No issue with that one. Actual voltage we are not giving. Yeah, it is in milliampere. Yeah, that is absolutely fine. Thank you. Thank you very much. Who have mentioned this one? Vignesh, you have mentioned this one?
Yes, sir.
Okay, thank you. Thank you so much. Actually, we forgot to, as we have already discussed in that if we keep both of the junction in reverse bias, then it will be in cutoff region. So initially our circuit there was a problem that all of this one means base emitter junction was also in reverse bias and this was also in reverse bias. So if all of them are in reverse bias, that is why we are having a current of femtoampere or something like that, or very less current, means that is also negligible. So that is why it is in cutoff region, you can say. And also this is the one of the good example that we can use a transistor as a switch. Means if you just flip the voltage means bias across this, and let's say we are keeping this bias fixed, collector base junction fixed, and if we just flip the bias of this base emitter junction, depending on that you will have a means switching condition between cutoff region to saturation region. Cutoff region means zero current, and saturation means there will be current flowing through it. So basically, you can use it as a transistor as a switch. So this is one of the case you can use it. Okay, now I think we'll have this base emitter voltage and emitter current. Now we can run it, and I think it will be different. The voltage, yeah, as you can see, voltage in millivolt. That is why the current is a milliampere. So if we increase it, okay, good. Now I think we can have the data that our everything is millivolt. Okay, let me increase this value at least. VCB, let's say for if VCB is the 3.1 volt, I think it will be in some millivolt. Then yeah, this is V1. Yes, this one, let me rename it. This is V1. Yeah, okay. This is okay. And for this one, we have 8.8 millivolt. Okay, now run this. Okay, so our VCV means collector base junction. Please, who is writing the data, please note it down. Now, for this case, VCV is 1.33 volt.
Yes, sir.
And for this one, we will have set of data for corresponding VBE and IE. So this is the value of IE, and this is the value of VBE. So make a table. Don't consider the negative sign because means it is due to that we want the voltage across it. Okay, and the negative sign is due to the biasing, as you can see from here. So if you have noted, then we can move further.
Noted, sir.
Okay, good. Now increase the potential to some different value, higher value. I think current is increasing. No, still it is in millivolt. Okay, please don't note down that value. We want to increase it up to 1 volt or something like that. Yeah, it is 1.11 volt and current is 11 milliampere.
Noted.
Noted? Oh,
Yes.
now let's take another value. Yeah, the current is 2.09. Sorry, voltage is 2.09 and the current is 15.8.
Noted, sir.
So as because we have applied resistor, so that is why we can go beyond means a different higher greater value of the resistor because there will be drop across this one and across that one also. So that is why net effective IB and IC will be different. Okay. So don't means I think make clear view on this one. Don't think that in case of virtual lab it was very less value and in this case we are having this match of value. Okay.
Noted.
I think again we are having some problem.
All are in negative, sir.
Yeah. Somebody just please tell me. I think again we are having problem because this voltage is also changing. It is why it is changing. Okay. Do one thing. This is the simplest thing we can do. Now it is good. Yeah. Please remove all the data from here only we will have. Okay. So our collector, sorry, emitter base junction voltage is 235 millivolt and the current is in picofarad. And we want to move it further. Let's say for 1 volt, 1.5 volt. Kilo ampere. don't know what is. Gigampere. No.
Sir, maybe because there aren't no resistors to limit the current. So it's shorted.
No, actually we have, okay. But in VLab we have applied resistor, right? But when we have applied resistor, then still it is, I don't know, it should not happen in this way. In VLab, I think you can see that if okay. It is in milliamps. Okay. It should be realistic. Otherwise, how it?
Social element.
Yeah, I think it is doing well. I think so. Yeah. Yeah. Now I think it is doing well. We can take the data. If we have only base limiting resistor in base, then I think we will have a good data for that one. Which okay. For this one, yeah, please take this data only.
Yes,
Yeah,
noted.
350 millivolt will have 79 picoampere, and let it be as 1 volt. Then for 1 volt, the current is 15.64 milliampere,
Noted, sir.
and 1.5 volt. 1.5 volt current is 62 milliamps,
Noted, sir.
and let's have another data only as 3 volt.
Noted, sir.
Yeah, for 3 volt, we are having 220 milliampere. Okay.
Yes, sir.
Now, please tell me the data. We can plot it over here. Yes, please tell me VB in voltage and
Sir.
IE in milliamps.
So VCB value 3.1. Will you note it? VCB.
Yes. That is for 3.1. Thank you.
1.5.
3.1. Okay. Please tell me.
1.5 volt.
1.5.
Yes, sir.
Okay.
62.52 milliamps.
Oh, before 1.5, there was no point.
Yes, sir. We took.
Means which is less than 1.5 volt.
We took 1, sir. 1 volt.
Uh-huh.
1 volt you took, sir.
Okay. 1 volt.
1 volt 15.64.
15.64. Okay.
Yes, sir. And shall I mention that millivolt also? You took one value of millivolt.
No, no.
Okay, 1.5, 62.58.
Okay, and this one,
And next 2.95,
0.95.
205.8.
Okay. Only these three data.
So 3.1,
Okay. Mm-hmm.
220.83,
Okay.
4.7, 4.75.
Which value you are telling?
Yes, sir, same. This B value. B value.
4.75.
75, 386.02.
386.02.
Yes, sir. That's it.
So this is 228.3.
Yeah,
Okay.
220, no, sir, 220.83.
Oh, sorry. 220.83. Okay, let me plot it. It's not showing that exponential nature. From where did you get that? I think we have less data, means we have considered less data, right? I don't, this is the maximum value we have considered. So did you simulate it on your own?
No, sir, whatever this is.
Okay,
That's it.
erase everything, then please note down from the beginning, I think.
Okay, sir.
Let's say our first point is 500 millivolt. Sorry. So for 500 millivolt means 0.5 volt. For 0.5 volt, the current is 25 nanoampere. Okay.
Yes, sir.
Now let's keep it as 1 volt. Okay, now for 1 volt, the current is in milliamps. I think it will be, yeah, it is 15.647 milliamps.
Notice.
Okay.
Notice.
Now for 2 volt, we'll have less data, but still will is, yeah, as you can see, for 2 volt only, the current is 111 milliamps.
Notice, sir.
Okay, then for, let's take another value only, 3 volt. For 3 volt, it is 210.85 milliamps.
Notice, sir.
Yeah. Now please tell me this value in this case. Please tell me. 0.5 volt and corresponding current is?
25.12 nanoamperes, sir.
Sorry, 25 point?
12 nanoamperes it is.
Okay,
For
25 nano means in milli it will be 10 power minus 6. Okay.
Yes, sir. Yes, sir.
Then
1
1
volt,
volt. Yeah.
15.64.
15.64, and then for 2 volt.
2
Yeah.
triple 1.52.
Triple 1.52.
52.
Okay. Next.
Next 3 volt.
Yeah.
210.85.
210.85.
85. Yes, sir.
8. Okay. Now we don't have any other value for this one. Let's see our graph. Yeah. This means we are having less number of data for lower voltages, but still you can see it is exponential nature. So let me, yeah, if we just make it as a, if we have another means a different set of data in smaller ranges, then I think we'll have that exponential, exact exponential one. So some sort of, you can say, will have different exponential nature is there. So it is quite similar with that we'll have one. Okay, is it clear or any doubt? If you have, then please ask me. So basically, as you can see that in this case, as you can see, depending on that biasing, means positive and negative, that is also very important. So in this case, they have means we are simulating on here in VLab. It is not clear from us from here that what should be connected to the positive terminal and what should be connected to the negative terminal. So once we do it here, so then we can understand what was wrong. So that is why these circuit simulators are very good, because it will give you real life examples. Means if we want to make the circuit for that means let's say in lab, then what will happen means you have to connect to the positive terminal of the battery to some let's say collector end or emitter end. So what you will do, so in that case, so that is why it is very good, you people can use it. Okay, so do you have any query till now? If you have any query, you can ask. Otherwise we will perform the output characteristics. So do you have any query? Okay, I don't think you people have any query. Okay, in case of output characteristics, what will happen? We have to consider, means keep the emitter current as fixed in milliamps. So we can fix the emitter current by changing the this RH1 with this rheostat. So if we change it, let's say for emitter current 1 milliamps, we want to have a set of data for VCB, means a collector current, as a function of collector base junction potential. So please note down the data. Means, oh no, these things you don't have to note it down. I can directly have the data from here. Okay, so our VCB is 0.88 volt, and we have currents in milliamps, 0.7, and for 1.58 volt the current is 0.92 milliamps. We are increasing for, let's say, for 4.5 volt of base collector junction potential, we have 1 milliamps current in collector. And let's say for another, let's take another final value for 9.78 volt across the resistor, across the collector base junction, we have this much of current, only 1.007. So as you can see, it is saturated, current is saturated. So we can have this nature from there. We can see it for different set of data, we can see it. My screen is visible to you, that graph plotting window?
No, sir.
Now it is visible, right?
Yeah. Yes, sir.
Yeah, okay. Okay, so for this set of data, in this case, sorry, I forgot to write down this one. This is VCB and this is IC. collector current in milliamps, and this is collector base junction voltage in volt, and IE emitter current is what we have considered 1 milliamps, right? So it is 1 milliamps. So for this set of data, we can plot. Okay, let take another set of data for different value of emitter current. Then we can plot them. So if we want to, let's plot it. If it is working. No. Oh, it is working. Good. So as you can see, we are having this saturation curve, means that we have initially for collector emitter junction. Basically, the same set of same type of curve we are having in this case. So initially current was increasing, current is increasing, and then after a certain value, it remained constant. Okay. So now let's clear all the value, and let's consider the collector emitter current as, yes, 2 milliamps, and let's have some data, similar data for. So we will have another set of data for, in this case, emitter current we have considered as 2 milliampere, and similarly we have considered, means change the voltage across the collector base junction, and we will see what will be the current through the collector, or collector current. Okay, so now, so the negative voltage we will not consider here, and this will not consider this negative value. Apart from that, we'll plot them. And for this case, we have considered that we'll take this two data only, then we can comment on that, is what kind of nature it is having. So in this case, it is 2 milliamps. We can comment on that. Now let's plot it. Yeah. So as you can see, this is the similar variation, similar we found it in case of common emitter mode. So basically, after the current is increasing at 0 voltage, current is increasing, and so depending on that, there will be some linear and non-linear region, and there will be some saturation region. You can see. So basically, depending on that, you can comment on, means if we keep on increasing that collector current, so you can say what will be the different set of data for this case. So this will be the smooth variation of the output current in this case in common base mode. Okay. So do you have any query? So I think we can simulate this over here. Yes. So for that one, what we have to measure? We have to measure the collector current and this collector base voltage. So we need another current meter or ammeter, you can say. It is lagging a little bit. Save your design. Yeah. What is the problem? Okay, now I think it is fine. Okay, let me refresh it. I don't know, there is some technical issue. And I think you can do on your own on the that common collector one. Okay, I think it will be better if you people perform the common collector one in the multisim, and in the next lab you can show me that corresponding input and output characteristics. You can plot it on your own. Several plotting softwares are there. Okay, now we do not need this voltmeter. Only these three things we need. For this one, let me check what is the emitter current, and this is emitter current IE, and this probe 4 is IC, and this is VCB. So let me run it once, then we'll have clear picture. Okay, IE is in 210 milliamps. Okay, let me reduce the voltage. No, please don't note it down. We have to reduce the IE, then only we can have means different plots. Please wait a minute. That is also higher value. Means actually in this case, initial we have to keep the IE constant. Okay, it should not be in nanoamps. It should be milliamps. Then only we can have. Let's say keep it in 1 volt. Okay, now it is fine. Yeah, for this IE value, we will have the set variation of VCB. Okay. Okay. Please note down that IE is 5.3 milliamps. Okay. Now we will vary the VCB. So let's start with millivolts means 0.5, 0.6 volt. So VCB in this case is 0.6 volt, and the IC is 5.27 milliamps. Okay.
Yes, sir.
Now if we increase the value, so 1 volt. Yes, if it is 1 volt, then the current IC is 5.277 milliampere.
Sir, it is same since 3 values.
Same?
IC value. It is same in the starting.
Okay. Let me check once, then we have to consider all the data for millivolt only. Let me check once. Means let me consider for yeah, it is saturated. So we have to deal with only in millivolt region, then we will have that particular.
Noted, sir.
Yeah, if it is 0, remove all those data. Now from this one, if it is 0 volt, then still we are having a current.
Same value, sir. Yes, sir.
Okay, this thing should be in reverse, right? Same thing we are having. Collector current. Why it is so? Let me reduce it to further. Value. Let's say for this one, our IE is in nanoamps. Yeah, then only we will have it. Now let me change it. Yes, let's say 50 millivolt, 500 millivolt. For 500 millivolt, I think there will be current. So still in nanoamps. Okay. Laughing for 5 will be saturated.
But IC and IAM, sir.
IC should be constant. Oh, it is. Okay, but still it is in nanoamps. That is due to that resistor rule. No. In nanoamps, it is saturated. Let me change this value to 200 ohms. Actually, that is due to this limiting resistor. You have to check. Let's say for okay, now the IC is in nanoamps, 372 nanoamps. I don't think it is saturated. No, it is saturated. So both of them are going to saturation region. We have made this one is forward bias and this one is in reverse bias. So, but still, why it is happening? We are measuring the voltage VCB across this one. Okay. Now, what will happen if we remove this? This resistor value. Let's zero. Resistance cannot be zero. In this case, also, I think 1.15 it will be, yeah, it is saturated. Okay, let's what we can do, we can increase this. I don't know why it is happening. Let's improve it to, I think now it will give some milliamps current. 1 point. Okay. Now I think it is fine. Current IE is in 1.85 milliamps and our IC is 1.84. Now increase this value. If we change this to 2.75, let's see whether it is saturated or not. No, it is. I think it is. I think it is that the value changes due to that of that limiting resistor. But I think it is saturated. Yeah, it's saturated. Okay. So actually, we have to control these two. Means when there will be current, means variation of these two knobs. If we have not selected a particular set of resistor, then there will be problem. So that is the main thing. IE is 1.74. That we have kept constant, right? Or it is also varying. It should be constant. Yeah, it is constant. The collector current is also now saturated. For 500 millivolt, it is saturated. How is it possible? No. Still saturated. No, it cannot be the case. Maybe there is some glitches. For 10 millivolt, how it would reach into saturation region? This is VCV. Yes, this is VCV. Okay. And this is collector current. Yes. And this is the emitter current. And for this case, we have kept it constant as IE as 1 milliampere, 1.74 milliampere, let's say. And if this thing, if we change the bias, I don't think it will work, because in this case, okay, it is not mentioned here, but voltage across base collector is positive. Yes, base collector is positive. Let's remove it, and I think it will work. Let me check once. Let's check the value. Okay, it is 5 volt. IE is 41 point. So that was high value. Let's change to 1 kilo. And I think now it will be under control. Yeah, it is 4 milliamps. IE. IC is 8.37. Now I don't think it is saturating. Yeah, now it is changing. Okay, now Vignesh, now you can take the data. So for this case, our IE is IE value is changing or not? No, I don't think it is changing. It should not change. IE value is changing.
No, sir, it is changing. But
Yeah, but IE should be constant. As because we are keeping constant the VB base emitter junction, we are keeping constant, but still it is changing. Let's say it is 1 volt. For this case, IE should be remain constant. I don't know why it is affecting. Okay, this current is good. Now IE is constantly changing. Means keep on changing. This should not be the case. Maybe there is some issue. I don't means I cannot figure it out right now why it is not means why IE is changing. Initially, we have seen that in the parametric plot that if we keep on changing that VCV, it should not affect the IE input current, right? So, but still it is changing. I don't know why it is changing. Means maybe due to the problem in this platform. So anyway, we have done this same thing output characteristics in that VLab one. I think you can understand the nature of the curve in this. Means it is nature of this curve. It is like this. So if it is working, then I will show you in the next lab. I don't know why it is not working. I will figure it out and I'll let you know in the next lab. Also, it will be very helpful if you people can figure it out on your own. Yeah, what is the exact problem? Okay. So till now we have done these things, common base mode, and I think in next lab we'll have that common emitter as a uh, common emitter as a amplifier. I think that was there. Yeah. Yes. Yes. I think it is there only. And other thing, it is not in our means curriculum. So I think we have only common emitter mode as a amplifier one in the next lab. This one, BJT common emitter as a amplifier. And also I think another experiment I have seen. Yes, CE as an amplifier. It was there. It is there. Okay. So do you have any query? Yes, we have another lab, LCR meter and C amplifier. So do you have any query regarding this common base mode that we have performed today, that input and output characteristics? Then you can ask me, or else we can conclude our session for today. Anyone, do you have any query?
One of the probe we should connect.
Your voice is not audible, please.
Hello.
Yes.
Hello.
Yes, yes.
So means we should connect emitter in reverse bias and collector in forward bias, right?
No, precisely you cannot say depending on that. Means without knowing that circuit configuration. Means let's say for common emitter mode, we have kept that.
Sir, I'm asking for common base.
Okay, in case of common base mode, we have to in input characteristics and output characteristics for both of the case, we have to keep this emitter one is in for emitter base junction is in forward bias, and collector base junction is in reverse bias.
Okay.
Okay.
Yeah.
Okay. Anyone, do you have any other query? You can ask me through the chat, or directly you can unmute yourself and okay. So I think we can conclude our lab for today. Thank you. Thank you very much for attending the lab, and see you in the next lab.